Hello everyone, welcome back to Electronics Prepper, the channel where we try to learn as much as possible about electronics, to become more self-reliant to technology and prepare for the future. A while ago, about a year or so, I made a video called Chip Differential Probe for Oscilloscopes, where I basically presented to you how we can build chip differential probe, because the commercial products that are on the market, in my opinion, are just way too expensive, at least for us hobbyists and amateurs. And most of the times we don't really need super high quality and high frequencies to work with. We just need, let's say, 1 megahertz maximum frequency, and decent quality would do fine. A decent quality differential probe would do fine. And because there are no such things on the market, I basically started to design my own and to build my own, inspired by someone else out there on the internet who also did something similar. Now, one of the this was the kind of project that attracted a little bit more attention from some people. And one of the viewers asked me at some point in time if I could help him create a signaling circuit that would basically let him know if the input voltage is above or below a certain threshold, so that he would know that he should no longer fully trust the signal that he actually sees on the oscilloscope, because it's over voltage or under voltage. The input voltage goes outside of the range of voltages that my differential probe can work with. And it took me a bit of time to think of something, test the circuit on breadboard, but here it is now. And this is what I want to show you in this video. It's basically a continuation to the previous video that I will link in the description in case you haven't seen him or you're interested in him, how to build a chip differential probe for our oscilloscope, for our small amateur electronics lab. This circuit that I will present to you in this video comes to basically add this new function to the existing circuit. So I will not go, of course, over the entire circuit that I've done back then. I will just mention a few things, and then I will explain to you the circuit, and I will also show you how this circuit works in practice. Although I have to mention that I have only created the circuit on the breadboard. I haven't actually created him on an actual board, because I personally don't care about having over voltage, under voltage detection. But even just on the breadboard, he works pretty well, at least up until 1 megahertz. So if you're interested in learning more about this particular topic, keep watching this video, because yeah, we will basically enhance this differential probe a little bit. Now, before we dive deeper, please allow me to say major thanks to the sponsor of this video, which is PCBWay. PCBWay is a leading PCB manufacturer that can help you build your dream projects, no matter how advanced they are. They can create just the PCBs for you, or help you as well solder components on them through PCB assembly services. If you're creating a full device, they can also help you create a plastic case through either 3D printing or injection molding services, or even CNC machining if you need custom metal pieces for a metallic case. You're free to use your favorite design software, upload the Gerber files, and one of their professional representatives will contact you, offering you one-on-one customer service. All you need to do is go to pcbway.com. The link is in the description. Thank you very much, PCBWay, for sponsoring this video as well. So right now, let's get started with the circuit that is going to basically light up a LED when the input voltage has gone above or below a certain threshold. Let me just quickly show you the schematic of the chip differential probe, because we need to remember a few things. First of all, we were powering this differential probe from initially from a 26 volt power supply. I had here a rather rudimentary step-up converter from a 9 volt battery all the way up to 26 volts. And then because we need to have actually a differential power supply, we basically split this 26 volts into 2 halves by creating a virtual ground with one of the op-amps. Also, part of the differential probe was what's called an instrumentation amplifier with 3 op-amps, 3 other op-amps. And we will be, whatever we will be doing at the very end of the last op-amp. So the very last stage of amplification, we will take the signal from here and inject that signal into another circuit. Okay, so this is all we needed to remember: the fact that we basically have a plus minus 13 volt power supply, and the fact that we have here, right before the output, we have an op-amp, which is actually configured as a differential amplifier, right? And a 50 ohm resistor, but that's besides the point. So let's start from here, okay? Now I have created a separate schema just for the sake of, you know, making it easier. Everything I have on the left of this interrupted line is whatever we had in our existing differential probe, and whatever is on the right side is the circuit that I will show you today. And I will also demonstrate how he works. Okay, so I have placed here 2 batteries to symbolize those 2 power supply voltages, plus minus 13 volts, and this is the last op-amp, okay, the one from here, U1D. This is the one, of course, without the other resistors and the other components, because we don't care. We also have the 50 ohm resistor that goes straight to the output connector, and we will be needing first of all, we will be needing, obviously, the power supply voltages along with the ground. And we will also be needing this particular voltage here, right at the output of this last op-amp. We will take him, we'll take her, the voltage, and inject her into the rest of the detector schema, okay? So, in order to remember one more important thing, I designed my differential probe to be able to have a maximum of plus minus 8 volts on the output, okay? So, no matter the attenuation factor times 10 or times 100, the output voltage cannot be higher than 8 volts or lower than minus 8 volts. This is so that we can fill the entire screen of an oscilloscope while having 2 volts per division, because we have 4 divisions up, 4 divisions down relative to the middle horizontal line. So therefore 2 volts multiplied by 4 equals 8. Okay, so this is what we have, or this is how I designed my differential probe back then. So what we have here is essentially a buffer that takes the attenuated signal and sends this signal forward to two different comparators, but they are not they're not your usual comparators, okay? And the reason why they are not your usual comparators is very simple. So the absolute simplest solution that we might think of is to just place two comparators just like that, and place some let me show you. If I am to draw this separately, okay, place two op amps, inject the signal into each op amp's input, have a reference voltage on the other. So let's say we are duplicating okay, so let's say we are adding a reference voltage on the inverting input, and the input signal we insert it into the non-inverting input of the op amp. Whenever the signal will go above the reference voltage in this particular case, then the op amp's output will go to the maximum possible output. So if we, I don't know, add an NPN transistor with a resistor, but I won't draw him, we will be able to just turn on that transistor, and that's it. And when the input signal will be below this reference voltage, then the transistor will be turned off, because the output of the op amp will be going down to the as close as possible to the negative power supply voltage, and that's it, and we can have a LED be, again, I'm not drawing the current limiting resistors, but you can imagine they are there. This transistor will turn on or off the LED, and the LED will make light, and that's it. However, we have a bit of a problem. And of course, this works only for the positive voltage. We would need to do something similar for the negative voltage as well. And we would do something similar, but we would flip things around. So let me think. Of course, we would need another voltage, reference voltage that is negative, and yeah, we would probably insert that voltage into the minus. So this is the ground. Okay, we would probably insert that negative voltage into the minus, and let's see. Or into the plus input, and then the input signal from the probe into the minus, something like that. I'm not 100% sure, but I don't want to waste too much time here. And we would through separate resistors, we would connect the outputs of the op amps to the same transistor, or perhaps two different transistors, doesn't really matter all that much. And this way we would turn on and off this LED. But such a solution would be very, very bad from the perspective of the speed that will be required to between when a spike comes on the signal and when the LED actually gets to be turned on, because of what is called the slew rate of the op amp. So the slew rate basically means the speed with which the op amp's output voltage can increase or decrease. And the slew rate is given in volts per in voltage over time, basically. Typically volts per microsecond, but it can have different multiples or submultiples for both the voltage and the time, but it doesn't matter. The idea is that if we would conceptualize slew rate, we would have basically a graphic. On the x-axis we would have time, on the y-axis we would have voltage, and the output of the op-amp would not be able to, you know, instantly switch from one voltage to another, because that's impossible. That would break the laws of physics. Whenever we want to increase or decrease, because it works both ways, the output of any op-amp, really, this output would increase linearly over time or decrease. But again, this would happen linearly over time. And the bigger the distance in voltage that we want the output to have, the more time, okay, so let me do it this way, the more time we would require to allow the op-amp to get to that particular voltage. Needless to say, we want to react in this detector circuit, we want to react as fast as possible. So in order to react as fast as possible, we need to limit the range of voltage that the outputs can have. Okay, we don't want the outputs of any comparator to go all the way close to the 13 volts of power supply rail or down close to the minus 13 volts. That's a 26 volts. Okay, the op-amp that I use, it's not rail to rail, but let's just, you know, simplify the discussion. Assuming it would be rail to rail, he would need to swing his output 26 volts, and that's quite a lot, and so he would require quite a significant amount of time. However, we don't need 26 volts in order to turn on or turn off a bipolar transistor. We only need 0.6, 0.7 volts. So by requiring only a small increase in voltage, we can have a much smaller time, so therefore a much faster reaction for this circuit that we are creating. Okay, so instead of choosing such a very simplistic but very bad solution, we have to think of how exactly can we limit the voltage excursion of each comparator. We will need two comparators. One that will compare whether we are whether our signal goes above 8 volts, and another comparator that compares if our signal goes below minus 8 volts. I'm talking again the signal on the very output of the entire differential probe. Okay. So, well, first things first, we need to stop working with plus minus 8 volts because it's too much. It's a bit too much. We need to work with less. So I've chosen to work with plus minus 1 volt because it's simple. We have a 13 volt, plus minus 13 volt power supply, at least in my case, okay? We can simply create a voltage divider with a 12K resistor, which is a standard value, and a 1K resistor, which is again a standard value. This will have a ratio of 1/13, and therefore this will give us 1 volt, precisely 1 volt. So we would have a voltage divider between the ground and the positive voltage rail, and another voltage divider between the ground and the negative voltage rail. And this will give us 2 points of plus minus 1 volt, and we will take these as reference. Now, of course, we need to compare this with an attenuated version of our output signal, which again goes from plus to minus 8 volts, so we need to attenuate this signal by a factor of 8, so that from a maximum of 8 volts we get to 1, and from minus 8 to minus 1. Okay, so we take the output from this last op-amp of our differential probe, and we send the signal to a voltage divider, another resistor divider, right, that has a factor of 1 to 8. So if we add a resistor here that you know, has a certain value, and a resistor here that has 7 times that value, then we have achieved this attenuation factor. Okay, we need to buffer the signal because later we will need to pull up and down. At least one of the comparators will need to, you know, pull up and down that particular pin, that particular input. So we don't want to basically have a negative impact on the overall functioning of the circuit, and so we need to buffer this attenuated signal. Okay, and this attenuated signal goes to the two comparators that do the job. Now, these comparators are slightly different because they need to do different things from the perspective of the input signal. The upper comparator needs to compare voltages between 0 and plus 1 volt. The lower comparator needs to compare voltages between 0 and minus 1 volt. Both comparators need to provide on the output a certain positive voltage, but the first comparator needs to, you know, have, let's say, one logic on the output when his non-inverting input goes above 1 volt, whereas the lower comparator needs to provide also one logic, so a positive voltage on the output, when his inverting input goes below minus 1 volts. Okay, so for this reason we have slightly different circuits. On the upper side we have two diodes in anti-parallel, two just simple rectifier diodes, 1N40, 148, placed in anti-parallel. And these diodes basically make sure that the output voltage never falls below minus 0.6 volts approximately, and never goes above plus 1.6, give or take. So we have a maximum excursion of, let's say, give or take 2.2 volts, which is a lot better than 26 volts, and therefore it will happen a lot faster. Okay. Let me make a print screen and start to draw a few things so that I can better explain what's going on in this upper half of the circuit. So, like I said, this comparator is meant to compare voltages here, okay, that go between 1 volt and 0, because they are referenced to ground. Okay, anything between 0 and 1 volt, he needs to stay, he needs to keep his output voltage at a certain voltage that does not open the associated NPN transistor. Anything that goes above 1 volt, he does need to jump as quickly as possible to whatever voltage is necessary to open this transistor. And this is why we have these two diodes here, that these two diodes connected between the output and the minus input, the inverting input, basically have the function of dragging up and down this input, and as well as keeping the output within just a diode drop, voltage drop distance away from whatever voltage we may have here. On one side, on one hand. On the other hand, as we remember from, you know, basic electronics, op-amps, especially when made to work as comparators, but op-amps in general, they will make it so that they will try their best to have both their inputs at the same voltage. Okay, so if we are sending this attenuated signal voltage directly to the non-inverting input and nothing else happens, because we don't have any feedback circuit that is connected to the non-inverting input. Okay, then whenever this voltage is lower than a maximum of 1 volt, the output of this op amp will be low, will be pulled down, okay, down to the ground, towards the ground. Well, he will reach and he will go even slightly below ground, but not by much. In this particular case, this diode will be blocked, okay, so it's as if this diode does not exist. This diode, however, does start to conduct, because we can have a current flowing from a plus 1 volt here into the diode, going towards whatever lower voltage we have here. So between when the input is between 0 and 1 volts, okay, the output will be anywhere between minus 0.6 and about 0.6 volts. So all the way to about 0.6 volts. Okay. Why? Because here we will always have a diode drop less than this point. Okay. This 1 volt point will be dragged down, of course, but he will not be dragged down lower than the other input. Okay, so I will show you a little bit better on the actual demonstration in a few moments. Okay, so this is how we get to keep the output voltage enough below the necessary threshold for the NPN transistor to open. Okay. However, when things start to happen in reverse, when the voltage on this input reaches 1 volt and goes above, okay, this point at the plus 1 volts point will no longer be dragged down. The output of the comparator will start to increase. At some point, he will not be able to drag down this point, because this diode will turn off. Okay, she will be reverse polarized, and this diode starts to become directly polarized, so she will start to conduct electricity. This point will be at a higher potential. Okay, so we will have here whatever voltage is on the input plus this 0.6 volts, that's just the normal voltage drop on the diode. And this switch from the previous state to this state will be quite abrupt, quite fast, which will be nice, because then so the first significant positive voltage that we will have, it will be 1.6 volts. That's when we will have 1 volt here, and 1 plus 0.6 equals 1.6 volts. Okay, so with 1.6 volts, of course, we can definitely turn on this transistor, because we will have 1 volt across this resistor. Okay, and the usual 0.6 base emitter of the NPN junction of the transistor. And this is how we basically have detected the overvoltage on the positive side, while at the same time limiting the output voltage of the op-amp himself, so that he does not need to jump 26 volts from one end to the other. Okay, this point theoretically should never go way above 1 volts, because it's impossible due to the other voltage dividers in the circuit. So as far as positive voltages go, here we will always have between 0 and 1 point something, 1 point just a little bit above 1. Therefore, on the output, we will this comparator will only go from minus 0.6 to a maximum of 1 point something, but below 2 volts. So only 2.6 volts, let's say 2.6 volts voltage excursion in total, which will be very nice. The speed at which he will move will be pretty fast, especially since TEL 074 has a pretty high slew rate. I don't remember from memory, but I'm willing to, I'm inclined to believe that was around 13 volts per microsecond or something like that. So, you know, 2.6 volts is gonna be less than a microsecond. So he could basically react faster than 1 megahertz to signals that are more than 1 megahertz, even though he will never need to do this because he will not work with you know, more than 1 megahertz. Okay, so that was on the positive side. On the negative side, however, things are a bit more complicated because, again, when the voltage drops below minus 1 volt, we need to make sure that the output goes high, goes 1 logic. Okay, so things need to work in reverse, and for that I needed to use a Zener diode. It doesn't have to be a 5.6 volts. Actually, I would recommend if you can get a 4 volt, 4 point something volts Zener diode. I didn't. 3 volt Zener diode was was just not enough. We would not get enough voltage on the output. 5.6, it's not bad, but you know, we could use a slightly lower voltage. But anyway, regardless of that, things work a little bit in reverse here. We are injecting a reference voltage of minus 1 volt into the non-inverting input, as opposed to the inverting input for the other comparator. We are injecting the input attenuated signal into the inverting input, this time through a resistor, and this resistor, he doesn't need to be 4.7K. I used randomly 4.7K. He can be less or more. He does have an effect, and I will tell you in a moment. The idea is that we need a resistor nonetheless, because this point sadly will need to be pulled up or down by this comparator. Okay, in order to limit the output voltage. Again, we are also trying to limit the output voltage excursion for this comparator so that he can, you know, move fast. Okay, so the idea is that whenever we have between 0 and minus 1 volt on the input, this this inverting input will essentially have a higher voltage, a more positive voltage than the non-inverting input, okay, which will make the op-amp want to drag his output down towards the ground, and he will actually do that. Okay, in this case, this output becomes more negative than the input. This Zener diode will be directly polarized, so she will allow current to pass, but she will keep only about 0.6 volts across her, because she will, you know, in direct polarization, Zener diodes behave just like rectifier diodes. So the output will be basically 0.6 volts lower than whatever this point is, and this point will be dragged down, but will not be dragged down any lower than -1 volt. So when the input is between 0 and -1 volt, the output will be pretty constant at -1.6 volts, give or take. So this transistor will, the associated NPN transistor will be turned off. Okay, he will not conduct. On the other hand, when the input voltage goes below, when the input voltage goes below 1 volt, okay, the reference voltage, which is on the non-inverting input, will be higher than this input voltage. So the op-amp will drag his output upwards as much as he can, and he will be able to drag this up to not quite but close to the Zener voltage, okay, above this -1 volt reference voltage, because again this point will also be dragged up by the Zener diode, but this point will not, once again, not be able to be dragged up higher than -1 volt. So on the output, when the input is lower than -1 volt, on the output we will have a positive voltage. Because the current that flows through here will be very, very small, and this current will depend on this resistor. So by decreasing the resistor, we will increase the current. This voltage here on the output, and basically the voltage across the Zener diode, will tend to not be the nominal voltage of that diode. Will tend to be smaller, okay? Because a typical Zener diode needs about 5 milliamps of current through her to actually give us the nominal voltage, or something very close to the nominal voltage, okay? If we inject a smaller current, then we will have a smaller voltage. However, the voltage will still be significant, that the output voltage, even though here we will have -1 volt, because this point will be dragged up, and this point will match this other point with a reference voltage, still the voltage on the output will be positive enough so that overall we will get a positive voltage. In my case, 3 or more volts on the output, when again the input goes below this -1 volt. And this will make it enough to turn on this associated NPN transistor. And here we have we basically have two transistors with the same emitter connected to ground, you know, each are being commanded by their associated comparators, and both of their collectors are connected together to a LED and a current limiting resistor for that particular LED. Because the requirement from this viewer was that we turn on one and only one LED, regardless of whether we have overvoltage or undervoltage. Okay, we could have had two LEDs, but he wanted just one. And this is basically how the entire circuit works for both the overvoltage and the undervoltage, and how we can keep things fast, okay, by using some diodes and some extra resistors to limit the output voltage excursion of these comparators. Okay, good. So now I hope that you have understood the theory. Let me quickly show you the practical results. So I have here, and I will stop. I have done 4 different tests, because of course this was easier for me to test things. First, I have tested the positive detector with DC. Then I will show you the negative detector with the DC. Then both detectors at the same time with a LED and a DC on the input. And finally I will show you an actual signal generated with a signal generator, and how this detection circuit would actually work, you know, for real. So here we have the positive detector with a DC on the input. With the blue multimeter we see the voltage that I was injecting on the input. By the way, when I'm referring to the input voltage, I'm referring to this one here after the buffer. So I was in order to make things simpler for me, I was working with only 0 to 1 or 0 to -1 volts on the inputs. Okay. This attenuator would be inserted if we would actually build this circuit in the end. So this is what we see here on the screen with the blue multimeter, the input voltage that will go from 0 to 1 and then a little above 1 to show you what happens. And we have the output of the comparator on the black smaller multimeter on the lower side of the screen. Okay, so at 0 volts on the input we see minus 0.6 volts on the output, and as we increase the input voltage, the output voltage tracks pretty closely this input voltage. However, we will constantly be below 0.6 volts, the necessary turn-on voltage for a typical, you know, bipolar transistor. Okay, so we see here at approximately 0.6 volts on the input, we have about 0 volts, of course, because we are always one diode drop lower, and we keep increasing this voltage. Okay. And this voltage, I'm gonna go back slightly, okay? So this voltage goes up to approximately 0.6 volts when the input voltage goes very, very close to 1. And then I'm gonna hit the play button, watch what happens when we when we are at around 1 volt, which is the threshold when you know, the detection circuit is supposed to trigger, and that's it. The output voltage has jumped very quickly to about 1.4 volts. And as we slightly increase, so now I've slightly decreased the voltage to see that the output voltage has fallen below 0.6 again. And now I'm increasing above 1 and something, okay? Now the output 1.4, 1.5, and as we move forward beyond 1 volt, we would see that, you know, the output voltage would track the input voltage pretty closely and would be at about 0.6 volts above the input voltage. Okay, so 1.6 on the input, 2.1 on the output, so basically about half a volt. Of course, in practice we would never achieve voltages higher than 1 volt by a lot, again because this is an attenuated voltage from our from the output of our differential probe, but I of course needed to test what happens. Okay, and of course when I would come back below 1, I would get very small values again, once again. So this is how the positive detector works. Now let me show you the negative detector. Here we need to work with voltages that are between 0 and -1, and the detection needs to happen below -1 volt. Okay, so here we have very close to 0 volt on the input, and on the output of the now we're talking right about this lower comparator, this lower circuit. On the output we have -1.7 volts. Like I said, we will always have about -1.6, 1.7 volts, which is -1 volt reference. minus the voltage drop on the Zener diode in direct polarization. Okay, I will start to increase the voltage towards the negative, so maybe I should say I will start to decrease. As you can see, the output voltage remains pretty constant, 1.6, 1.7, minus 1.6, 1.7, and soon I will go below 1 volt, and bang, as you can see. So I will go slightly back and play here at almost 1 volt. The output voltage jumped from minus 1.6, 1.7 to plus 2 point something, okay? And as we get just a few millivolts more on the input, we get an even higher output voltage, 3 volts, which is the Zener diode in reverse polarization, minus the 1 volt from the reference, but still a positive voltage, okay? And of course, if we would continue to go below minus 1 volt, we would keep having, increasingly higher output voltages, but we don't care all that much about that. So this positive voltage can definitely be used to turn on that associated NPN transistor, okay? And when we fall back above minus 1 volt, bang, we fall again on the output in the range of voltages that can no longer sustain a transistor turned on. Okay, and now let me show you both circuits. This time without an output voltmeter. I actually have a LED. So pay attention to both the voltmeter and the red LED on my breadboard. When the red LED turns on, of course, the circuit got triggered. So I will go from 0 to positive voltages, back to negative voltages, and I will go back and forth several times. So on the negative side, you see, bang, at minus 1 volt, the LED turned on. If I start to increase, the LED turns off. If I go on the positive side, between 0 and 1, the LED stays off. At approximately 1 volt, the LED turns on. And of course, if I would keep going, the LED would still remain on. And like I said, going back and forth, you can clearly see how the LED turns on only above 1 and below minus 1 volts. Okay, and since of course this circuit is not meant to work with direct current, but with alternative current at certain frequencies, let's actually inject a signal from a signal generator into the buffer and allow the circuit to work as expected. I have tested this at various frequencies, but on the screen I will only show you 11 kilohertz, 111 kilohertz, and 1.1 megahertz. In all situations, I have chosen, like you see on the screen right now, half a volt peak to peak, and I will play with the offset to have peaks that go above 1 volt and below minus 1 volt. In order to see those peaks, just take a look on the screen of the oscilloscope. On the right side, where you see this sinusoidal waveform, you can see the upper and the lower levels. So for instance, right now the upper level is 0.25, the lower level is minus 0.25 volts, okay? And of course, pay attention to the LED on the breadboard. So as I was increasing the offset, okay, Right now we have 0.85 volts. We're testing the positive threshold right now. 0.95, bang, 1.05, and the LED got turned on at 11 kilohertz. And now I'm going down. Okay, I'm going up and down a few times to show you the LED turning on and off. Now I'm going to the negative side, so watch this lower tag on the screen. It's right now minus 0.95 volts, and as I will go at minus 1.15, the LED turns on. At minus 1.0, the threshold apparently was at minus 1.06 volts. Okay, so of course you will need to be doing some minor tweaks to, you know, the reference voltages, the resistors used. I did not bother to actually create to actually choose good matching resistors. I just wanted to see the circuit work, so I didn't bother with a very precise values. Of course you will need to do this, but it's not a big deal. Okay, so now I have increased the frequency to 111 kilohertz, as you can see, and once again I will play with the offset 0.95, 1.05, and the LED turns on. 1.15, the LED turns on even brighter, and going negative, minus 0.85, 0.95, LED is off, and minus 1.15. Okay, so this time the LED turns off between minus 1.15 and minus 1.25 somewhere. Again, you can tweak the values of the resistors that you use in a circuit in order to, you know, better match whatever threshold you want to have. And now I have increased the frequency to 1.1 megahertz. By the way, this difference in thresholds, slight difference in thresholds that you will see, can also be done to potentially some attenuations of the signal that happen because I'm, especially at these relatively high frequencies, I'm just taking the signal through a crocodile cable that's not exactly meant to carry, you know, 1 megahertz cable signals. And so it is very possible that on the breadboard I actually have lower signal levels, and this is why I need to have higher or lower thresholds in order to you know, make the circuit work. So here on the positive side, this triggered between 1.15, 1.25. Somewhere around 1.2 volts positive, this seems to be good. On the negative side, we will go shortly. The circuit needs minus 1. Again, between 1.15 and 1.25. So yeah, somewhere around minus 1.24 volts the circuit gets triggered. So this clearly proves that with just a few extra components, you know, we can achieve this overvoltage and undervoltage detection. Honestly, I personally don't find this to be all that important, because we can just assume that by seeing more than 8 or less than minus 8 volts on the oscilloscope while using this differential probe, we can just assume that we cannot trust anything that goes outside of these ranges, and we don't necessarily need such a detector. But anyway, I have to admit that thinking and designing this kind of circuit was a nice, interesting exercise, because I've never thought about something like this. So yeah, this was well worth it. So I hope you've learned something new. I hope you enjoy. Thank you very much for watching. Many thanks to the supporters of this project on Patreon. Those of you who would like to support my work to learn more and come here and teach you more can do so on Patreon. Link is in the description, or for free, like and subscribe to my channel, especially if you want to see more of this in the future. Will definitely help the YouTube algorithm promote my work to other people as well. So once again, thank you very much for watching this video. I will see you soon in yet another interesting video that helps us on our path of getting prepared for, you know, various problems. See you later.